Sitting on the south bank of the River Tees in the northeast of England, the modern industrial complexes of Middlesbrough can be seen for miles. Close to the river's mouth and the North Sea, this stretch of water was, for centuries, shallow, tidal, and difficult to navigate. Standing here now, it's easy to forget that the river itself once dictated what could and could not exist on its banks. Long before the blast furnaces and cranes, this was a place shaped by mud, tide, and uncertainty. Until the early 19th century, the land here was largely marsh and farmland. That began to change after 1829, when the opening of the Stockton and Darlington Railway made the area viable as a coal exporting port. What followed was rapid and largely irreversible. Ironstone discoveries in the nearby Cleveland Hills accelerated everything. Middlesbrough did not grow gradually. It surged outward, driven by demand and opportunity. By the mid-19th century, the River Tees had been transformed. The channel was dredged and straightened. New docks were cut into the banks. Heavy industry arrived and then multiplied. Ironworks, steelworks, shipyards and chemical plants pressed in close to the water, each dependent on the river and competing for space along it. That growth created problems. Ships needed to reach docks farther upstream. Workers' carts and later motor vehicles needed to cross the river without stopping production. Machinery had to be proven safe before it was trusted in the field. Factories, railways, and shipping companies needed to agree on the same time every day. Today we're going to look at 4 mechanical structures developed to solve these problems. Not decorative landmarks, but working engineering responses to pressure. This is Rails and Revolutions, the history that built us, the forces that shaped us. We begin with the simplest question of all. How do you cross a working industrial river without stopping it? By the early 20th century, road traffic across the River Tees had increased beyond the capacity of existing crossings. Delays were no longer an inconvenience. They affected factory output, dock schedules, and the movement of goods moving inland and out to sea. At the same time, the river remained an active shipping channel, serving docks and heavy industry upstream. Any new crossing had to do 2 things at once. It had to carry road traffic efficiently, and it had to disappear on demand. The solution was a vertical lift bridge. The Newport Bridge opened on 28th of February 1934. It was designed by Mott, Hay and Anderson and built by Dorman Long. The bridge carries the A1032 across the 9 spans. The central lift span measuring 269 feet. The steel towers supporting that span rise to around 180 feet. And the total length of the bridge is approximately 807 feet. Steel cables pass over large sheaves at the top of each tower and connect to massive counterweights. These counterweights balance most of the moving span's mass, reducing the energy required to lift it. 2 electric motors rated at 325 horsepower drive the system, raising the span at roughly 52 feet per minute to a maximum clearance of about 121 feet above the river, enough for tall-masted vessels to pass beneath. The bridge was designed with failure in mind. If electrical power was lost, a 450 horsepower petrol engine could operate the lift. If that failed, the bridge could still be raised by hand. Historic records suggest it would take 12 men, roughly 8 hours, to complete a full lift using a manual winch. Originally, the bridge was run from a central control cabin. Operators coordinated with gatekeepers at either end, managing road closures, signals and lifts in real time. At the moment it opened, it was the first large vertical lift bridge in Britain and one of the heaviest of its kind anywhere. River traffic declined during the late 20th century. The bridge was last lifted in 1990, after which the span was permanently locked in the lowered position. Today, traffic passes across it without pause. Its machinery is silent but intact. The bridge is now Grade 2 listed, its steelwork preserved as evidence of how movement once had to adapt to industry. Not the other way around. Crossing the river, however, was only one part of Middlesbrough's industrial system. The town also produced machines that were never meant to stay here. Middlesbrough was not only a place goods passed through, it was a place where heavy machinery was imagined, built, and then sent out into the world. As engineering projects grew larger and more ambitious, the cost of failure increased. Bridges, cranes, and structural frames could not be corrected easily once installed. Components had to be trusted before they ever left the ground. That need produced a different kind of mechanical solution, one that did not move, but measured. By the early 20th century, Middlesbrough was producing increasingly large steel components for major engineering projects in Britain and overseas. Calculations alone were no longer sufficient. Steel had to be pushed, bent, and broken under controlled conditions, so engineers could see exactly how it behaved. To meet that need, Dorman Long built the Britannia Test House in 1926. Inside it stood what was then the largest structural steel testing machine in the world. The machine could accommodate members up to 50 feet long and up to 3 feet 9 inches square in cross-section. It was capable of applying immense loads, forcing components beyond their working limits, while engineers monitored stress, deflection, and failure. The building itself reflected that purpose. The ground floor was dominated by a hangar-sized test hall. At its centre stood a testing machine approximately 120 feet long, served by a 30-ton overhead crane used to position specimens. Entire structural members could be tested exactly as they would appear in real construction. What happened in this building did not stay in Middlesbrough. Before the Sydney Harbour Bridge was assembled on the far side of the world, its steel passed through this space first. Nearly 40 major components were shipped here and tested to destruction. Engineers watched how the steel deformed, how cracks initiated, and how failure finally occurred. Those broken samples were not waste. Each failure informed revised calculations and safer construction methods. For the men working inside the test house, this was not abstract work. A mistake made here would not remain local. It would travel thousands of miles and reappear later in a structure carrying trains, traffic, and people. The arch rising over Sydney Harbour depended, in part, on what happened on this floor in Middlesbrough. That pattern continued. As bridge spans grew longer and designs lighter, components and testing methods developed here informed projects such as the Forth Road Bridge, the Severn Bridge, and later the Humber Bridge. Middlesbrough became a quiet checkpoint in global engineering, a place where ambition was slowed down, measured, and proven before being allowed to proceed. During the Second World War, the test house supported defence projects, testing components critical to the war effort. In the decades that followed, its work expanded into civil engineering, aviation, and international infrastructure, reinforcing the town's reputation for engineering reliability rather than spectacle. In the mid-1990s, Durham Lifting acquired the test house and upgraded the facility, allowing it to remain in active use. Though rarely seen by the public, it continues a tradition established nearly a century earlier. Here, problems were not avoided. They were quantified, contained, and resolved mechanically. From force and pressure, we move to something less tangible, but equally necessary. Time. As Middlesbrough expanded, coordination became essential. Factories ran to fixed shifts, ships docked to tight schedules. Railways depended on precise timetables. Local timekeeping was no longer sufficient. The town needed a shared reference. The Middlesbrough hydraulic clock tower was built as part of the working docks. It was practical rather than ornamental, combining a water tower and clock tower in a single structure. The tower seen today dates from around 1903, replacing an earlier Dockside clock tower built in 1847. Its form reflects its function. A broad lower section housed water tanks and hydraulic accumulators. Above it rose a slimmer clock stage, visible across the docks and river approaches. The structure is built from red engineering brick with sandstone and terracotta detailing, topped by a slate-roofed clock stage. Inside the base, cast iron tanks stored water under pressure. Elsewhere on the dock estate, steam-powered pumps forced water upward into these tanks. From there, stored pressure could operate cranes, lock gates, and dock machinery on demand, eliminating the need for individual engines at each site. The clocks provided a shared time signal for dock workers, mariners, and tradesmen. One unusual feature is that the tower has clock faces only on 3 sides. The blank side faced the industrial yards, a deliberate decision to prevent workers from watching the clock instead of working. The tower also served as a navigation aid, offering ships approaching the docks both a visual landmark and accurate local time. Dock operations continued into the 20th century, but by the 1970s, the original dock system closed. The clock tower ceased its original function around 1980. Restored in 2005, it remains Grade 2 listed, one of the few surviving elements of Middlesbrough dock infrastructure, and a reminder that power, timekeeping, and navigation were once tightly linked. Yet even with clocks and bridges, one problem remained: crossing the Tees without touching it. By the early 20th century, traffic across the river had once again exceeded the capacity of existing crossings. A high-level bridge would have required long approach ramps, disrupting factories and docks. The solution was a transporter bridge. The Tees Transporter Bridge opened on the 17th of October 1911. It was designed by the Cleveland Bridge and Engineering Company and built by Sir William Arrol and Co. The bridge spans approximately 853 feet, with a main span of 575 feet. A gondola travels about 160 feet above high water, while the steel towers rise roughly 200 feet. Vehicles and pedestrians cross the river on the suspended gondola. Steel cables carry it along rails mounted beneath the fixed span, powered by electric motors housed in the towers. Each crossing takes around 90 seconds and can carry up to 200 passengers or 9 vehicles at a time. Mechanically, the design is efficient. Counterweights, rollers, and tensioned cables keep the gondola stable while in motion. Compared with conventional bridges, it required less material, caused minimal disruption to the riverbanks, and allowed shipping to pass uninterrupted. The bridge was Grade 2 listed in 1971 and remains one of the few operational transporter bridges in the world. Though closed in recent years for safety repairs, it continues to define the skyline and the character of the river crossing. Each of these structures answered a specific need during Middlesbrough's rapid transformation from marshland to industrial centre. The Newport Bridge allowed roads and ships to coexist. The Britannia Test House ensured machines could be trusted before they were put to work. The hydraulic clock tower synchronized a town running on shared schedules. The transporter bridge carried people and vehicles across the Tees without interrupting the river below. None of these structures was built for display. They were funded because the cost of not solving these problems was higher. As industry changed and river traffic declined, their original purposes faded. What remains is a record of decisions made at a moment of industrial confidence, shaped by economics, technology, and expectation. Looking at these structures today, we see more than engineering. We see how Middlesbrough anticipated its future, and how those solutions continue to shape its memory. Whether they are seen as obsolete or as part of the town's living industrial heritage is no longer just a historical question. It is a present one.